right, we're going to go ahead and get started here. Hi, everyone. My name's Ryan Fairfax. I'm an engineering manager at Microsoft working on the Azure Sphere operating system. I've been working on Azure Sphere for the last 3 years, doing everything from writing kernel drivers, bare metal firmware, leading the team that built the OS components, to these days looking at enabling Azure Sphere on new hardware platforms. And so I've been involved from the kind of beginning. And the thing I like to preface these talks with, if you had told me 5 years ago that I'd be building a Linux-based product inside Microsoft, I probably would have laughed at you. But it's been a fantastic journey, and I'm really excited to show what we've been doing and talk in a bit more technical detail about some of the stuff that Ed covered in the keynote this morning. So the agenda for today's talk, I'm going to give a very quick overview to some of the parts of Azure Sphere, a little bit deeper than what we saw in the keynote. I'm going to talk about the hardware just to give everyone an idea of the class of device that we're running on. It's more of an example than a fixed use case. Really the meat of the talk is going to be on the OS architecture and individual components. I'm going to spend most of the time talking about our work we did to the Linux kernel, but I will talk about our user space story. I'll talk about our boot firmware. We're going to cover all parts of the operating system. Then we're going to talk a bit more about the development model and what it looks like if you are a device manufacturer and you just want to write your app for one of these devices. And then at the end, I'm going to talk a bit about some of the stuff we're thinking about in the future and some takeaways that I think are relevant not just to the work we did, but also to anyone that's looking in the embedded space and the IoT space. So first of all, this is the slide that Ed showed in the keynote. When we think about Azure Sphere, when we talk about Azure Sphere, it's really a three-part solution. What I'm going to talk about in this session is a little bit on the hardware, mostly on the OS, but it's important to call out that our solution really only provides the level of value that we think it does when you consider all three together. And so I'm going to go deep on a couple of these, but it's part of the story, and I wanted to emphasize that before we get going. So let's talk about the operating system architecture. One of the principles that you saw in the 7 properties was defense in depth. And we really took that to heart when we designed the OS architecture. In a lot of cases, if you're running a traditional Linux setup, you've got some code in user space that is running daemons, applications, at different levels of sensitivity, but very similar in terms of actual hardware levels of access. You've got your kernel running in supervisor mode on a CPU. You might have a trusted execution environment or secure enclave of some point. We really wanted to go beyond that. And so we've got additional levels, multiple levels in our operating system that when we say OS, we talk about the entire story. We don't just talk about Linux. We don't just talk about user mode. And I'm going to walk through each one of these in detail as part of this talk. But to give you a kind of bottom-up view, we have at the very bottom, we have the hardware, obviously, the capabilities in the hardware and its boot ROM. We have our security monitor, which protects access to critical resources, and we'll talk in more detail about what those resources are. We have our customized Linux kernel, and I'll talk about some of the customizations we did. We have our on-chip cloud services, which are daemons and user mode services that provide update, device authentication, connectivity, network management, that kind of thing. And then lastly, we have our app sandboxes, and we have 2 types of apps on this platform. Applications that we call POSIX applications that are built using standard POSIX APIs, and they run on a Cortex-A. And then real-time apps, which can be bare metal or existing RTOS code and run on a Cortex-M. So let's start diving into each of these. So the first thing I want to talk about is the hardware. The main things that are critical in terms of what does it mean to be an Azure Sphere certified device is built-in networking. So the first chip that MediaTek produced, the MT3620, has 802.11 Wi-Fi, but obviously there's many connectivity options to the internet. Things like cellular, even things like Ethernet in industrial automation scenarios. We're not tied to Wi-Fi. It's just an example of the type of connectivity. The Pluton security subsystem, which is a combination of Microsoft-developed hardware and software, that forms the base of our trusted computing base. And the main thing that we're doing here that I think is different than a lot of traditional MCUs is a combination of Cortex-Ms and Cortex-As. And so Cortex-Ms for your real-time processing where you need high real-time guarantees, Cortex-As for network connectivity, more compute-intensive things like ML, that kind of thing. And so it's really a hybrid solution. So to give you an example, let's talk about the one chip that is available today that's Azure Sphere certified, MediaTek's MT3620. So to give you a sense of the hardware here, there's two different dedicated CPU cores. So there's a Cortex-M4 that runs the Pluton security subsystem that we'll dig into in a second. They have their own MediaTek developed 802.11 radio with dedicated processor. And then there's three cores for applications. There's the Cortex-A, it's an A7, it runs at roughly 500 megahertz. It's where we run the Linux kernel, it's where we run your apps that need to connect to the network, that kind of thing. And then there's two general purpose Cortex-M4Fs for customer code. And so we don't actually have anything running on that by default, and in fact, if you don't use them, they stay fully powered off. Microsoft wrote a bootloader to get your code onto it, and at that point, it's bare metal. So you can either go directly to the hardware, or you could, for example, port an RTOS, Zephyr, FreeRTOS, ThreadX, whatever your preferred platform is. And then there's a number of peripherals. I list them here. It's pretty standard stuff in the embedded world. Things like serial UARTs, I2C, SPI controllers, analog to digital, GPIO, PWM, the things you expect to see from a reasonably capable chip. One of the main things that I think is a little bit different for Azure Sphere is we actually map these peripherals to a given core at any point in time for security purposes. So we can say that only the A core can access this SPI controller for the moment, or only the M core can access this serial UART. And it just lets us make stronger security guarantees about what does a compromise let you do. And then the main thing to take away is the storage here. So we're talking 4 megabytes of total sysram. So we're booting Linux in around 2100K, 16 megabytes of serial NOR flash, and that 16 megabytes of flash has to include space for us to stage updates and other things, so it's not your firmware is 16 megabytes, it's actually quite a bit less than that. So let's dig into the software. That's the kind of primer, the type of hardware we have here. The real meat of this is the software. So at the bottom layer of the stack is our trusted computing base, the security monitor. And there's a couple components to this. But the main things I want to emphasize here is it's where we run security critical code. And then the natural question is, well, what does that mean? What is security critical? There's certain operations that we have on our platform that we've deemed are key steps to enacting a compromise. Power management, for example, being able to control what cores are running or what clock speeds they're running at for setting up things like differential power analysis attacks or glitch attacks. Writing to flash is a great example of a very security sensitive operation. If you can just go scribble over a bootloader, at the very least you could do a denial of service attack very easily, if not something worse. So we really have this set of security critical operations we wanted to be only inside the TCB. Even within the TCB, we have some layering. So we have some code on a dedicated core, that's the Pluton security subsystem that runs on a dedicated Cortex-M. We have some code that runs in a TrustZone-based piece of software on the Cortex-A. And they each have different responsibilities. And the main goal of our security monitor, the number one principle, is to keep it as simple as possible. Attack surface matters in your TCB, and it's really critical that you keep it as simple as possible so that there's fewer opportunities for buffer overruns, there's fewer opportunities for attacks and compromises with the defects in your software that can be escalated into something else. So these things are really, really tiny. To give you an example, so let's talk about the Pluton security subsystem. This is the most trusted entity in the system. It's the very first thing that boots when the SoC turns on. It's a dedicated core. That gives us a little bit of side channel resistance, and it makes it easier for us to reason about certain life cycle things. Like I said, when you power the chip on, it is literally the only thing running. It has to release the rest of the processors. It's a custom bare metal firmware. Now, we looked at RTOS options, and there are many with different levels of capabilities. We decided pretty early on we didn't want a system that supported threading. We wanted to minimize interrupt usage so it's a bit more predictable so we don't have complicated reentrancy. And we didn't want any kind of application model inside this. And so because of that, we decided to go bare metal, simply to go as simple as possible. The main things that Pluton does is it drives our secure boot. And so it's the one that is verifying signatures of further next stage images and loading them into RAM. It hands off execution to the Cortex-A core. It does measured boot, which is really key to our platform. So we're not just saying this piece of software is signed by a key we trust. We're actually recording that in an irreversible manner inside some custom hardware so that we can prove to the cloud later we booted with this set of software in this very particular order. And the cloud can decide, yeah, that's good, or hey, wait, you're running a version that has a known compromise. I need you to go update before you talk to the rest of services. And in terms of security-sensitive operations, authentication and attestation, so it's the only thing that can access the private keys for the device's identity. In fact, well, actually, it can't even access the private keys. It can only leverage them. It can do sign with the key. There's no way to actually even extract the private key or read it into RAM. It does power management, like I talked about. There's a lot of impressively clever attacks using power gating and power analysis. And so that's one of those things that I think is far more security sensitive than a lot of people realize. It does image verification, and it does trusted key management. And so we negotiate some keys with the cloud while we're running for things like TLS connections and authentication, and it manages those inside its secure RAM boundary. Just above that is our TrustZone security monitor. Now, I'm sure with this audience, a lot of people are familiar with TrustZone, but just as a quick primer, it's an ARM technology that splits basically a Cortex-A or some of the newer Cortex-Ms into two worlds of execution, what they call normal world and secure world. Each of those worlds has their own supervisor or other privilege modes and user modes, and it's really about being able to run a secure OS or a trusted OS and a normal world OS simultaneously. So we use this to run some very minimal pieces of software on the A core. So we're time slicing with Linux. We context switch in and out based on a few things, some interrupts, and mostly actually calls from the Linux kernel. And so this is the only thing that can write to Flash. And so when Linux is going to commit data to Flash, you've touched a file on the storage medium, it actually calls up into our security monitor via TrustZone state transition. And we can access check and say, hey, is this appropriate? Are you writing to the right region? Is this a region that this app's allowed to touch? We also can do things like detect attacks by trying to hammer program erase cycles and otherwise physically damage the hardware, given a lot of these Flash technologies has a very limited number of writes before the hardware starts to decay. The main thing in our current design is that only secure world or normal world is executing at any point in time. They're mutually exclusive. It's a full state transition. We don't run them simultaneously. Now, part of that is the first chip is a single core A. It's not SMP. But it also makes it a lot easier to reason about from a security perspective. That does mean these calls have to be very, very fast, milliseconds or less, because you're basically freezing the Linux world while this is happening. And in terms of things that this part of the software stack does, it does peripheral access control. So it's what decides that your app can access these GPIO pins. And you may say, well, why is that super critical? So think of an application where I've built a device that has two main functions. There is an LCD that is my user interface and maybe a knob and a button where I'm entering my Wi-Fi passwords. And then there is another GPIO that controls a solenoid that actually physically actuates the device. And may, if you over actuate it, may actually physically break something. You want different levels of access control on those different pins, even though they're both GPIO in the traditional sense. And so the security monitor can actually restrict access to individual cores of saying, this block of pins is accessible by this core, this block of pins is accessible by this other core. And that way, if there's a compromise, it limits the damage you can do. The main thing the security monitor does is it runs our update engine. So it's what lays out software on Flash and boots into new software. One of the core principles of our update engine is every piece of software is updatable. Bootloaders, secure firmware, Linux, everything, because we know there will be bugs to fix in all of it. There'll be new security issues, there'll be new features, and it's really important you just have a story of I can always update. Writes to flash, we talked about that. One thing to note there is reads are not protected, because that's critical for your performance. And it divides up the RAM for use by various components. And so it can carve out a block of that 4 megabytes of RAM and say this is a secure buffer, carve out a block and say this is what Linux sees, that kind of thing. Okay, so above this we have what we call the high-level OS kernel, but it's the Linux kernel, right? And we use the term high-level OS because especially when you're talking with people that are used to real-time OSs, you need to distinguish between the two modes. We started from the kernel.org sources. When we started 3 years ago, we started on 4.1. We moved to 4.9 about a year in. We're actually in the process of moving to 4.19 right now. That early investigation has begun within the team this week. And our goal here is to keep rolling forward. We don't want to pin to one branch. Linux is doing so much work so quickly, and they are making fixes and adding features and bringing on new hardware platforms at an incredible pace. And it's really important that we're able to leverage that, to take advantage of the fantastic work the community is doing, and to make it easier for us to collaborate with them on new features. And we've just found that if we pin to an old version, all of that becomes very, very difficult. So we actually pull in the point releases, the upstream patches, approximately monthly. Sometimes we do it a little bit more quickly. We don't ship them any faster than monthly unless there's something really critical, a CVE that's high impact or exploited in the wild. But we're trying to stay up to date. And we've made some modifications. So we have about 350 commits on top of the main line. The vast majority of those are like 1 or 2 lines, and they're tweaks and optimizations. We did an incredible amount of just make this buffer smaller. The best example that resonates with me, the kernel's designed to be able to handle 1 million processes at a time. And so they have a hash table of PID to task struct lookups that is optimized to hold 1 million entries. 1 million page tables does not fit in 4 megabytes of RAM. That's just way overkill for what we're doing. We have on the order of 30 processes active at any point in time, or 30 threads. And so we tweaked that hash table. We reduced the size of it and instantly clawed back kilobytes of RAM. And when you're talking 4 megabytes, every kilobyte matters. So we have a lot of patches and just optimization. We turned off entire features in the kernel. We block a certain number of syscalls just because they're not relevant to a kind of IoT device that doesn't have an interactive shell and doesn't have user management in the traditional sense. And of course, we've got some hardware-specific drivers for the MediaTek board, some tweaks to the security components that I'll get into in a second, that kind of thing. So our biggest challenge when we started was actually just making this fit. When we first built this, the actual kernel binary was like 4.1 megabytes, which if you have 4 total megabytes of RAM is a real problem. And so we just spent a lot of our first year really just squeezing and identifying areas to make this smaller and fit within our envelope. First thing we did is we moved to execute in place, so we don't pay the cost of the code in RAM. We're running directly off the serial NOR flash chip. That saves, megabytes instantly. And so that once we did that, we were able to boot. We were able to get inside our memory envelope, but we still had problems. I talked about some of the patches we did, making things, tuning size of caches. We made some things modular that weren't modular before. There's a general attitude that I think I totally understand, and in fact even did multiple times in my career before I took this role of like, you're building a kernel drive and you say, yeah, I'll just allocate a 256K buffer, no one will even notice. But when that's 1/16 of your total system RAM, you notice. And so there's a lot of just optimization we had to do in the kernel for decisions that make perfect sense on desktops and servers or even phones, and just don't work on the lower end of IoT. We did cut some features to reduce size, so we don't actually start sysfs. It's amazing how much the strings in that add up in terms of RAM overhead when you're counting bytes. We turned off some memory tracking options. We're not shipping symbols inside the kernel, so okay, all sims is off, that kind of thing. Where we got to is at our when we launched our public preview, these numbers are a little bit out of date. I actually think they're slightly better now. But we were at roughly 2.4 megabytes of code for the kernel and roughly 2100K of heap and stack usage after boot. So this is boot all the way up through in it's about to start. We were at 2100K. And given that we started at, I think the first build, we just barely fit in 6 megabytes. We've been pretty happy with the progress we've been able to make. So some of the other customizations we did some security work here. And We actually prototyped a few things. I'm going to start by talking about something that we ended up not shipping, but I think it's interesting to show the way the thought process evolved. We started by actually using static permissions, and so we baked things into the file system when we built it. So in our rootfs, we had the SUID and SGID bits set on files to make apps launch as very specific users and groups. We baked capabilities into the file system using extended attributes, and we relied on the kernel basically to guarantee that when they launched processes, they came up with this context. The great part about this approach is it was very easy to reason about final access control. Auditing was just a matter of walking the file system. The problem is that we found that it was hard to actually make flexible enough for what we needed. We found cases where a customer application, not all of them need access to the same parts of the system. Some parts might not need to be able to set the Wi-Fi SSID and password, for example. But if you're building an onboarding experience, if you're building an LCD display to enter your credentials, you do need to be able to set that. And so we ended up with this whole set of permissions and capabilities, and we found that baking them into the file system was very difficult to get the right permutations and combinations. And even more than that, it became even harder of, well, now if someone's uploading an application to us, we have to reason about, did they accidentally set the root UID bit and say, I want to run as UID 0, then we have to reject it. There became a whole trust challenge and verification challenge with third-party code that we just didn't want to deal with. And so we took another stab at this. The second version, and the version that we're still running a variation of, is we said, okay, we're going to build a very simple Linux security module. And the idea here was to enable very specific access control points on certain operations above and beyond what the kernel gives you with their capability system. So we added a couple fields to every process. We added this, what we call component ID, but it's really an identifier for the app. So what application is this process associated with? We added a network ID, and that's mostly used in device authentication to know how to auth to a cloud endpoint. And we added an extended set of capabilities, and these aren't the standard Linux capabilities like capnet admin. These are new things we added to our system about things related to peripherals and our update engine, who can request updates, that kind of thing. And then the idea is we sprinkled through a very targeted set of kernel hooks the ability to use these fields in their access control in addition to the traditional UID, GID, and mode bits that you see in most Unix access control. The other thing that we did with this is we made everything immutable. So once you set a component ID, once you set a tenant ID or a set of capabilities, it inherits to all child processes and you cannot change it. This is really important for us to be able to reason about security guarantees. We don't have the kind of scenarios where we don't have the equivalent of an SU in our system where you're going to change user. The next area that we did a lot in the kernel is we experimented a lot with file systems. We talked about execute in place, so there's some somewhat well-known patches floating out on the internet to add execute in place to CramFS. We forked that slightly to reduce some overhead and throw away some modes that weren't relevant. We patched in copy on write support for execute in place so that you can actually do debugging. That was one of the first things we realized is that GDB, when you set a breakpoint, it likes to rewrite the code. It inserts an illegal instruction and then traps it. And if you're execute in place, those writes just get dropped by the memory bus. And so we actually patched in the ability to do copy on write in a few situations to keep all the rest of that functionality working. And we really spent a lot of time looking at writable file systems. There's a lot of file systems, log-based file systems that you see on embedded devices, JFFS, that kind of thing. We even looked at ext2 for a while and said, is that appropriate? And we found they all kind of had either too much RAM overhead, they had to load all of their inodes into memory, or too much flash wear overhead. Like an ext2 wasn't designed for a system where program erase cycles matter. And so we actually ended up taking LittleFS, which is an ARM effort that is open sourced on GitHub, and we ported it into the Linux kernel. And in fact have had some conversations about how to give that back to the community even, because there's very little specific to us in that. But we found it was a great file system that had very little overhead, was designed for flash devices, so it understands wear leveling and understands the differences between erase sizes versus program sizes, that kind of thing. It's been pretty successful for us, and it's a great example of something where we want to leverage the community's efforts and really build upon it and contribute back. So the last point I'll say about the kernel is we added more access control. I think the best example, the most obvious example, right now the kernel assumes that you either have access to all GPIO pins or not. It's a node in /dev, and your permissions are basically can you write to that node? Can you send an ioctl to that node? And we wanted to be able to split it up in more detail. We wanted to be able to say pin 1 is accessible by this app, pin 2 is accessible by this app, pin 3 is not accessible at all. And so we added some stuff to the GPIO infrastructure and a few other peripherals. We did some slide extensions, really tiny, to add these extra access checks. We added file system quota support for MTD block devices, for flash devices, because we want to, again, guarantee that an app can't just take up all the writable space on the file system, and then you try to update your Wi-Fi credentials and it fails because you're out of space. And we adjusted some items specifically around capability checks to make them a bit more granular in a few places. There's quite a few things in Linux, especially when you get down to bus level peripherals where they just assume, oh, you're root, you just need to be root, or have cap sysadmin. And we wanted that to be split up because we wanted no cases where you had to be root in our system. In fact, nothing runs as root. Even our init process switches off of root immediately and drops a lot of its capabilities. So that's an overview of what we did to the kernel. Let's talk about user mode a bit more. What we call our OS services, our on-chip cloud services, it's really about services to support applications and services to support app development. And so libraries, daemons, development tools. Most of this is existing open source tech that we've just cross-compiled or made minor tweaks to. So our libc is the muscle libc library that's popular in a lot of embedded devices. We're using curl for network traffic. That kind of thing. Names you would all expect to see in Linux and embedded Linux. We customized where we needed, mostly around size constraints. Like we're not running systemd just simply because it was too big. And in some cases around attack surface. So let's look in detail here. So our user mode model is really focused around applications. Everything is an app other than what we call the application manager, which is our custom init process. This includes all of our system services. So we don't have a special model for the network manager versus code that a device manufacturer is writing. That's important because we actually found it was a good way to force ourselves to be honest and make sure if we're building the components that we need and the security models that we need to do the most sensitive parts of the OS, in general, we have all the right components for device manufacturers to do the same operations. Apps are self-describing. They run, they're independently updatable. So you can ship an update for just a given app. They generally run isolated from each other. Some of them have IPC endpoints. And so your network manager has an IPC endpoint to get the current state of the network or add a set of Wi-Fi credentials, that kind of thing. And we have 4 out-of-box system apps. And so we have our network services that manage mostly credentials, honestly, and Wi-Fi state, turning the radio on and off. We have our command and control endpoint, which is used for development and diagnostic scenarios. It's so when you're cabled into a PC, you can load apps on, you can get logs off, that kind of thing. We have our update services, which are mostly handling the check for updates portion and the staging of images. We jump off to the security monitor once an update's staged. So this is really just about downloads and talking to the cloud and getting data on what should I be running. And we have some hardware crypto and RNG acceleration, a daemon that integrates with the actual underlying hardware that we have. And then lastly, we have an optional GDB server. So if you're doing local development, if you've got a device that you've unlocked for development, we load on a copy of GDB server so that you can connect that up to your favorite IDE. And the main thing here is that apps are renewable. These aren't baked into a file system somewhere, into a rootfs or into a sysroot. Everything can be updated over the air. We manage all of the system updates, and so Microsoft is producing updates for all these daemons, the network services, that kind of thing. And OEMs are in charge of the app updates. They decide when it's time to push an update to their app, how they want to partition one app versus many apps, that kind of thing. So let's talk a bit about how we got to where we are on our app model. So we originally looked at, okay, we knew early on we wanted it to be self-contained. We wanted apps to be a unit that you could easily basically stop, unmount, replace, remount, start, versus a kind of traditional model where you would install binaries into user bin or user lib and that kind of thing. So we naturally thought, okay, great, containers feels like the right solution for this. And we spent a lot of time trying to make containers fit. That was quite a summer. A lot of debugging and trying to make it squish and fit. We looked very seriously at LXC. We knew Docker was going to be too big very early on, but we thought LXC might be big enough, but we just could not figure out how to do it. And the reality is, especially with containers, you're presenting an alternative view of the network, so you have a secondary network device, a bridge network device. You have an alternative view of the file system, so you're remounting file systems, and all of that stuff adds up in RAM very, very quickly. And so it had such an overhead that we just couldn't get it to work. We actually looked at rolling our own using the underlying namespace functionality in the kernel. Then we hit limits where a number of the peripherals for low-level buses are not designed to be namespace aware. GPIO, SPI, I2C, and that's really important to the type of apps people are writing. So we kind of shelved this for the moment. Now, I wouldn't surprise me if we get back to namespaces eventually in some form. I don't know exactly what that looks like, but it's something that we keep talking about internally as something that's interesting to us long term. So what we did instead is we said, okay, we want apps to be self-describing. Let's create them as self-contained file systems. That solves the update problem in terms of it's very easy to unmount, update, remount a self-contained file system. And so when you build an app in our platform, you're packaging up this file system. The file system is actually what you upload to the cloud or send to the device over a USB cable. And it contains your binaries. It contains any data file, static data files that you need, things like certificates. It contains a manifest, a JSON file that describes your application. And so that metadata drives the rest of our engine, and we'll look at that in a second here. So here's an example piece of the metadata. It basically describes a couple things. It says what to run, so what's my entry point? What app do you want me to launch? It talks about policy to enforce, and so you can see in the capabilities section here on the right, there's a set of allowed connections, and we actually program the NetFilter firewall to block all other traffic from your app, and that is, the idea there is if you get compromised, if you have a buffer overrun, what does a botnet developer want to do? They want to go hit their command and control endpoint on the web to say, who should I go target? And by putting the firewall in and saying, no, you can only talk to who you normally are supposed to talk to, we've immediately made that harder. It talks about what peripherals you have access to, and it's denied by default. So if you just put a blank manifest in, you've got computation, and that's it. You don't have access to any peripherals. And we enforce all of this with things like cgroups. So we use cgroups for resource limiting, RAM quoting, CPU limiting. We do give every app its own unique user ID and group ID just to make it easier to integrate with existing Linux and Unix security. We update permissions on dev entries appropriately. I talked about programming the firewall. And like I mentioned earlier, every process other than init's an app. So we use this for OS services in addition to OEM applications. And so one of the last remaining principles here in our user space is we wanted to reduce our attack surface by simply removing features. So the best example is there's no shell. Just the act of having a shell causes you to have to do a lot more threat modeling and thinking about, what is my attack surface here? How do I protect against this? What tools am I shipping with the shell? Are they properly secured? And we just didn't even want to deal with that, especially because if you think about an IoT device, they're often headless or a minimal display. Shells and account management aren't relevant in that world. That also means we block some of the syscalls that are needed to do shell scenarios and things like session management and that kind of thing. There's no kernel module support. Again, once you have kernel modules, you have to reason about how do I trust the code that I'm loading into the kernel. We weren't convinced that we could do that in the times that we had, and also kernel modules and execute in place are a challenge all in of themselves. And we ship a really reduced library set. So there's 9 shared objects in userlib. Compare that to your Ubuntu system that has hundreds or thousands in some cases, and it's just a greatly reduced attack surface. We also limit resource usage with cgroups, and so RAM exhaustion is predictable. You don't just get into a situation where I try to malloc a megabyte, there's not a megabyte available, a random process gets killed. We really wanted predictability more than anything else, because without predictability, you're going to get into a situation where update no longer works. You can't get out of the problem. And we talked about apps can't access network traffic or peripherals without opting in. So that's a kind of high-level overview of what we've done in the OS. I want to talk a bit about some of the future items that we've thought about, and a little bit about takeaways, and then we'll have a few minutes for some questions. So the first thing that I know we need to work on more is figuring out how we upstream some of our work that is generally applicable. Some of the optimizations we did for size are just as applicable to a desktop as they are to an IoT device. Now, not all of them are that category. There's a reason they had that hash table of process ID translation for 1 million for your server. But there's some clear wins here that we actually think could be useful to the general community. Our file system work is, I think, generally useful to a whole class of range of devices. Things like that. We want to look at more namespace usage. I talked about this a little bit earlier. We know there's still opportunities there and great security goodness if we can figure out how to make it fit. We want to look at splitting up some of the stuff like capsysadmin. Linux still has, in a few places, a very monolithic security model where you are highly trusted or not trusted at all. And we think there's opportunity for more granularity there. And the best example is there's an assumption that certain hardware features are low level. If you want to access the SPI bus, you must be root or a highly privileged user, because on PCs and desktops, you just don't do that often outside of management activities. We think there's a real opportunity there to revisit that and enable those kind of scenarios for embedded devices in general. And kind of the last item I have here that we've been talking about on and off for, feels like a year and a half now, is trying to figure out how we can leverage more security features that are in the kernel that are too big today. And so things like SE Linux or AppArmor, I've had some fantastic conversations with some people about that, of trying to brainstorm about how could we take the foundation they have there, figure out how to modularize it and make it fit in the RAM envelope that we have, because there's just fantastic work going on in the Linux community when it comes to security that I think the embedded community could really benefit from. One of the things I tell security experts, I actually gave a variant of this talk at the Linux Security Summit, and I said, when you're designing an LSM, when you're designing something like AppArmor or SE Linux, you're often not thinking about what's the memory overhead. You're thinking about purely what is the threat model, what am I protecting against? And so you've got your large caches and all the things you need in RAM to make your feature. And I think we're starting to see a shift, and I think a lot of the developers agree that they're going to actually also think about, okay, how do I make it fit in the envelope of embedded? And of course, there's far more ideas than I could ever possibly fit on one slide or in one talk. I think we come up with a new idea about once a week that is interesting. That's part of the exciting part of working in this space, is there's still a lot of unsolved problems. So the takeaways I like to share with folks, the number one thing that I think, if I've learned one lesson in the last couple of years, it's security and resource usage are often at odds. Features are designed for strong security. They don't think about space. They're often all or nothing. You get all of SE Linux or none of SE Linux, for example. Now that's not true. I'm generalizing a bit. It's not true in every case, and I'm seeing actually some great movement in new work to try to be more modular. But it puts us in a situation in embedded where often we can't take advantage of some of these features without paying for everything. Where really, even if we could just get some small feature of it, it instantly up-levels the strength of the product. The other takeaway is there's a lot that just works well. I mean, Linux has largely dealt with our insane plan to make it run in the amount of RAM from the late 90s that desktops had at that time, and it's largely done it without too much complaining. We had to squeeze and optimize, but it works, and it's reliable, and that is, I think, a fantastic testament to the work that the community's been doing to make sure that Linux runs on a very diverse range of devices. Most changes we made are small. That's the best indicator, honestly, more than anything else. Like when we merge in a new set of changes from Linux, we don't have merge conflicts, and that is the best feeling. And then, the last takeaway that I think I would share with this group is that the improvements in the desktop and server space, which is where you see a lot of development going on, a lot of energy going in, often help embedded in IoT. And so, the security work that they're doing, if you take a step back and you look at the fundamental problems they're trying to solve, they're there and embedded in IoT as well. And so the problem space we're facing is far from unique. And so there's definitely a lot of opportunity to continue that collaboration, to figure out how to build features that can benefit both worlds, resource constrained and otherwise. And I think that we'll continue to see the trend where the innovation that's happening in the operating system world, the hardware world, the cloud services world impacts both big iron desktops, laptops, and phones, embedded, IoT, all the way down to sensor devices. Okay, with that, I've got a link here to some of our documentation and samples if you want to see what it's like to actually build for our platform that you can look at offline, and I've got a few minutes for questions. We got one up here.
Thank you. Great presentation. Thank you. With respect to the processor itself, are you using 64-bit or ILP32?
32 only.
32 for code size or mostly?
Yeah, it's mostly size. I mean, with 4 megabytes of RAM, 64-bit pointers really hurt.
And with respect to memory usage, how do you know when to stop? I mean, at some point it becomes a problem of diminishing returns, right?
If you know the answer to that, I'd love to know. I think we're all still learning. You're right, there is diminishing returns. Very early on, we had a ton of wins because there was low-hanging fruit. There were things that just was obvious, we can make this better, we can shave 256K here or there. Every win we get at this point is much harder fought. It's a combination of two things. We look at how much RAM we have and try to reason about, do we have enough to continue to grow? It can't just be your process today fits, because we know there's more features we want to add. And we're also trying to get more data on how much RAM do device manufacturers need for their scenarios. I can reason about how much RAM the OS needs. It's a lot harder for me to reason about what is the device manufacturer part needs. And so it's something where we're pretty consistently investing in shrinking, because I think there's always work to be done, but I don't know if we'll ever call it done.
A final question. You work with Microsoft, so you have access to Windows and the source code, and you can easily modify it, right? So why did you choose Linux over Windows? And you don't have to answer it if you don't want to, but I'm interested.
We'll see if I can get this right without getting in trouble. No, honestly, the main reason is the open source nature of Linux. It's when you're building with a device today, there's an expectation of open source. And oftentimes these devices, especially like silicon vendors, if we're working with MediaTek or we've announced a partnership with NXP, they already have Linux drivers. And we want to be able to really leverage that and take advantage of that versus saying, okay, you've got to jump onto our platform from scratch.
So on the application or applets, are you what sort of are you planning separate tooling just for the applets themselves from your Linux development environment?
So right now we have it is slightly different than the environment that we use for OS development. I'll say that, though the gap is closing. So when we first launched, we had a Visual Studio-based development environment using some of the Visual Studio Linux development tools that have shipped over the last couple of years. We've leveraged, lately we've added support for CMake-based builds, which is much more flexible. And we're looking at continuing to expand that to meet the needs of what people need in their development environment. But at the end of the day, the code is Linux. That's actually built with a version of GCC that we produce, and we ship a version of GCC. It's got a couple tweaks and optimizations, again, for size more than anything else. But it's a tool chain that would be familiar to a lot of people.
This relates more to the Pluton environment, but has there been any work on formal verification and getting certification through some of the government bodies for that low-level part?
Not that I'm aware of, but my focus has been more on the software side than the hardware side, so I don't want to say it isn't happening, because it very well might be. But I haven't seen any formal verification efforts. We've talked about things like FIP certification for random number generation and things like that, but haven't gone very seriously down that path yet.
Thank you.
For the memory size, it seems that it all stems from having SRAM instead of DRAM. So the decision to go with SRAM, was that based on the power budget that you have, or some security concerns, or something completely different?
That's a good question that I don't know if I actually know the original answer to, because a lot of the chip specs that MediaTek had come up with had kind of solidified at the time I joined the project. Obviously, depending on the memory technology you use, you could have significantly more RAM. DRAM could be, even cheap DRAM could be in 32 or 64 meg chunks, which is pretty significant. And part of our strategy is honestly to let the silicon vendors decide a lot of what their price point they want to hit, what technology they want to include. Now, the nice things about the SRAM and the MediaTek chip is it's on die. It's a lot hard to tamper with versus an external module where you could cut traces or put them in the middle. So I think the actual real decision will be, what attacks do you want to protect against? Do you care about physical tampering or not? And so, I think that's something that over time we'll see a range of options there if I had to guess. And the thing that I like thinking about, if we build an Azure Sphere chip with DRAM with, let's say, 128 megs of DRAM, it's going to be very optimized. There will be a lot of RAM for use for customer applications because of all the work we've done. And so I feel like we laid a really solid foundation that can really expand to larger memory setups.
So I understand the licensing model for Linux and the applications on top of that. Mm-hmm. What about the source code and licensing for the Pluton system and the secure monitor?
Yeah, for the moment that is closed. I think there's been a lot of requests for us, to open that up, and I think that's something that we'll have to talk about internally. But I can't make any promises on policy.
2 slides back, when you were talking about next steps, you were talking about upstreaming the parts that you think would be relevant for other parts of the ecosystem. What about the parts that are just for your product? What's the resistance, or what's blocking actually mainlining those things as well?
That's a good question. I think there's a couple factors. Part of it is we haven't had time to think about upstreaming some of the driver work that was done that was hardware proprietary. And it's not a lack of desire to do so, it's just where we are in our maturity cycle as we bring this online from public preview to general availability. I will say there are some changes we made that I suspect would be rejected or at least require significant rework to hit the main line, to be much more configurable. And it's not that I don't see us doing that one day. It just hasn't been our focus. I think let me put it this way, I think there's some low-hanging fruit that wouldn't have a lot of resistance to get into the main line. And so that's where I've been putting my energy in, thinking about what would we upstream next. But we're shipping all this software publicly. We're posting it, it's GPL. And so we're trying to make sure that we are meeting all of our obligations there and doing it right, shipping build instructions and tool chains and that kind of thing. So there's nothing sensitive, secretive, that kind of thing.
So will you be releasing a GitHub tree or the set of patches in addition to just a integrated tree?
It's a good question. Right now it's just the integrated tree published on, Microsoft maintains a site where we publish our OSS sources to make it easy to search by product and that kind of thing. I see the value in shipping either GitHub or patches, but it's just not something we're set up for right now.
Thank you.
Okay, I think we're out of time, unfortunately. Are we over? We might have time for one more. Oh, does it not start for 12? Got it. Okay, good. Good. Then we can do another.
I was curious about the IPC you mentioned between the applications. Is that something that's custom or has kernel implications?
Right now, it's between applications and system services, and so it's IPC for things like configuring networks. It's IPC for we have some IPC mechanisms to request deferral of an update, for example, to tell an app there's an update available, and you can say, wait, not right now, I'm in the middle of something, schedule it later, that kind of thing.
But the actual implementation, does it have any kernel?
It's a Unix domain socket at the
Okay,
end of
all
the
right.
day.
Just wanted to see if it was a custom thing.
We did not want to reinvent that technology.
So I noticed that the kernel version you adopted is far from the latest kernel version. So what make you to do such choice?
Our general strategy has been we stick to LTS branches. And at the time that we moved to 4.9, it was the latest. Now, we've sat on it a bit too long, to be honest. We got buried with other work, and so we're actually looking to move to 4.19, which is, I think, still technically the latest, though I suspect they'll declare a new one shortly in the 5 series. 5.4. Yeah. So we'll move to 4.19, and then I suspect we will try to move much more quickly to 5.4 once it's there. Our goal is roughly to move once a year, major versions.
Okay, thank you.
Another quick one. As far as I just historically, I feel like people have given similar talks on strategies they've used to reduce down to very small systems. Sure. And I think having some stats on this over time is very useful. And so something I was kind of curious is, as you've moved to newer kernels or you're evaluating 419, have you seen growth in areas? Is there anything that you can kind of provide to the community?
I can only talk about, so the 419 move is in the very early stages, so I don't have data. I think we literally started it Friday. The 4.1 to 4.9 move was about a 15% jump in size. Now, we were able to get most of that back by looking at new config options that are on by default and that kind of thing. But there's been a growth path pretty traditionally, and I expect there to be growth as we pick up new versions. The hope is just that a lot of it is new modules we can turn off or that kind of thing. But we are leaving ourselves room to grow, because we know if we don't have at least a few hundred K we're holding for, the kernel gets bigger, we're going to be in trouble.
Hi, it seems that you started with a 4 megabyte magical number and then looked at what can we do within this constraint. Did you ever take a step back and say maybe 6 or 8 is the right number instead of 4? And I'm thinking particularly in terms of containers that you had to eject that as part of that decision.
Yeah. Part of it was dictated by the chip design that we were targeting and the cost. At the end of the day, it's the price they want to hit, right? Especially with SRAM, where it's on die, where you're talking area impact that turns into dollars very quickly. I think we were pretty confident pretty early that we could do this in 4 megabytes. I think there's probably additional security strength that could be added with more RAM, more compartmentalization, more defense in depth. And that's something that I think is really interesting to think about as processes get smaller so that you can get more RAM in the same area, that kind of thing. I mean, the MediaTek chip is 40 nanometer. At 28, the price is considerably different, because RAM dominates the footprint. We prototyped with more RAM early on, just when we were trying to convince ourselves, is this even possible? So we did spend a lot of time early on saying, is this just are we just going to hit a dead end, a year into this project? And we were pretty confident we can make it work.
I guess related question would be, do you see yourself creating a different security and deployment model for bigger footprint like with DDR in the future?
It's a good question. I don't think we've done enough thought to have a conclusive answer to. I think we have to consider, what do we do if we have more RAM? But we just haven't gotten to a point where we've been able to put the right due diligence into, is that the same model? Is it a different model? Is it layered where extra features come in, that kind of thing?
Okay, thank you.
Okay, I think we should
take a break.
We should close and have a 2 or 3 minute break before the next session.
Thank you, everyone.
Thank you.